Hey everybody, welcome to Bill Sky, the Assembly Guy, and we're going to do loops today. Now, if you looked at our processing arrays video in assembler language, you've already been exposed to one of the loops. I'm going to go through that again, but also when you look at C and C++ and Java, and I mean just any language, Python, they have all these different loops. Why do they have all these different loops? Because loops are tools to process data, and that's basically what a computer program does. That's what an algorithm does. If there was no such thing as data, there wouldn't be any purpose for it. So loops repetitively process data, massage it. That's a very large part of data sciences. And so how's that actually done down at the assembler language? When a compiler has a for loop, how does that actually implement it in assembler language? And why is that important? Because that's what a compiler does. A compiler will take a C, C++ loop, it'll convert it to assembler language, machine language, and then that way the computer can do the loop. So that's what we're going to do today. Let's get started. Okay, so what I've got here is that I've got a number of different loops. I have a 32-bit, actually I think it's a 64-bit Linux assembler language application open. Now, this is exactly the same on Windows. Okay, the only reason I'm using Linux is that it's faster, it makes it a little bit easier, quite a bit easier in a lot of ways, as you've heard me say, doing development. So I'm going to do it on Linux, but it is completely transferable towards Windows. I can't think of anything that doesn't work on Windows when it comes to loops. It all does the same thing. So what I've got here is I've got a program that has a number of different loops. We're going to go over the standard loop, which we already did in the processing array video, and then we're also going to do what you see here is a simple while loop in C++. We're going to do a do while loop, which you can see right here, and then we're going to do a for loop. And I'm also going to introduce you to this idea of negative logic to make your code smaller. So let's go ahead and take a look at that, and the first thing we'll do is just the standard loop. So what is the standard loop? In assembler language, in Intel, a standard loop is really just a loop that counts down. So what you do is you move into a register, in this case RCX. If you're on 32-bit, you use ECX, and we put a loop counter in there. And I'm going to use decimal for the loop counter just because that's how we think. So decimal 10 means a loop is going to execute 10 times. And what we normally have to do is we have to say, let's call this standard loop. You have to put a label there. And then you have to put a loop instruction and tell it where to loop to. And that's the loop. So the way that this works is that RCX in this case is given a number 10. Everything inside of the loop is executed, and then the loop statement says, let's subtract 1 from RCX. If RCX is not equal to 0, go back up and execute this loop again. It's just a jump up there. Now, when I do this video for ARM, there is no such thing as a loop statement, so we are going to have to do actual jumps. So a little bit more involved, but that's how that standard loop. It always counts down. It never counts up. Now, one important thing to do is that if you don't initialize RCX, you're going to get a loop that might loop 4 billion times plus. Why is that? Well, if we have a 0 in RCX, what does the loop statement do? The first thing it does is subtracts 1. So if you take 0 and you subtract 1 from it, you get a negative 4 billion. Or I think you get a positive 4 billion. Because excuse the use for the word loop, but it overflows or it underflows to the highest value that in this case, and actually it'll be 80 gazillion. I mean, that's not real, but it'll be huge, right? So it'll go back, and then it'll count down from there, and then when it reaches 0, it'll end. So it's very important to put a loop counter there. Put something in RCX, and then the loop will happen. Now I'm just going to put a no-op in there, and I'm going to build it. And let's go ahead and watch it run. And what we're going to do on this is we're going to use the debugger because we didn't really print anything. I guess I could have printed out ECX. We're going to see that later on. But what I'm going to do is I'm just going to put a breakpoint on the move 10 and I'm going to run it. and we're just going to step over and watch it. Now, what we're interested in watching is ECX. So we move 10 to ECX. There's our 10. We loop. It's now 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And now it dropped out. So what happened was it subtracts 1 from RCX, and then it checks to see if it's equal to 0. If it is, it drops out. Now it doesn't check to see if it's equal to 0 first before it decrements ECX, or RCX in this case. It decrements RCX first and then drops out. So that is the standard loop. We could have printed off ECX. What I could have done is I could have said push RCX and call print 64-bit num decimal, and then call print NL. These are using the Komanetsky functions that I provide to you guys. So let's run this and we'll see it decrement. And there's the decrement. It goes from 10 to 1. Okay? So that's how the standard loops work. If you want more details on that, go ahead and take a look at the processing arrays video I have for assembler language. All right, now I'm going to comment all these out because we don't want to have to go through and step through all that when we debug it again. So I'm just going to comment that out. So let's do the next thing now. The next thing will be the standard while loop. Now let's look over this while loop really closely. So what I do is I create a variable called x. It's an integer. I make it equal to 0 while x is less than 10, because a while loop has a condition. And this is a pre-test loop, which means it tests the condition first and then it does what's inside the loop as long as that condition is true. So while x is less than 10, x is initially 0, so 0 is less than 10. It'll then see out x, it'll increment x, and then it gets down to the closed brace and it jumps back up and does the while loop. Now x will be 1. Is 1 less than 10? Yes, so it outputs x, and so forth. So if you don't understand this loop, maybe you need to go take a look at some of my C++ videos on loops, because they explain very well how these loops actually work. So I'm going to assume you understand how that loop works. The important thing to remember here, though, is that it is a pre-test loop, which means it tests a condition before it actually does the contents of the loop. So let's go ahead, and I've got a little print here where I'm printing a simple while loop. So I'm going to print that notification, and if you take a look here, you can see it right there. Now I put those prints there just to better display the contents to the screen. Okay? So let's go ahead and let's do that loop. So what is the first thing it does? It moves 0 to x. Now the other thing I did was I created a variable called x, or I created a memory location called x. I reserved a single quad value in the BSS section, and I also did a variable I. We're going to use that for the for loop later on. Okay, so we need to move 0 to that. Now we can't assume that has a value, so I'm going to move into x, and we want to say a keyword 0. So that basically does that. So I'm going to put a comment there, x equals 0. Now it did not create x like line 42 in the C++ commented code did, but we moved 0 to x there. So let's go ahead and build that and make sure that's okay. All right, good. So that's the first line. The second line is the while. So now the while is the condition, right? So we have to compare x with the number 10. So let's do that. So I'm going to compare a keyword x with the number 10. And let's first of all see if that works. I don't believe it will. You got to do something a little bit more complicated than that. And actually it looked like it built. That's pretty cool. So we're comparing a quad word in memory at label x with the number 10. Now in previous versions of the NASM assembler, you'd have to do something like this. You have to move into RAX 10, and then you have to compare RAX with a keyword. Actually, no, I think you had to do this. You had to move into RAX, X, and then you would compare RAX with 10. That used to be what you had to do. But it's kind of nice. There's multiple ways of doing this stuff. Let's go with the the first way, but that's another way to do it. And so I'm going to do the while x is less than 10. So what's the next thing we have to do? We actually have to make a decision here. So if x is equal to 10, so I'm going to say jump equal to, I don't know what we want to call this. Let's call this continue while loop. So if it's equal, I want to continue the while loop. Otherwise, what I want to do, I want to leave the while loop. So I'm going to say jump, leave while loop. Then we have to create the label here. We have to create the label for leave. And now we're going to do the contents of the while loop. And I always like to indent that. So what does it say to do? It says to output x. So I'm going to move into RAX the value x. I'm going to push RAX. And then I'm going to call print 64-bit num hex or decimal. I'm going to call print and L. And what am I missing here? Okay, so that is the inside of the loop. So I'm going to go ahead and document that to count x and L. So that's what all that code is doing right there. Now, if you're not using my functions, you have to write all that code yourself to output the data. All right. And let's go ahead and put a little semicolon there to show that those two lines of code. All right. Now, what do I have to do now? Well, we have to increment x. So I'm going to say, now RAX contains x. It may not contain it after this. So let's see if we can increment a keyword starting at x. Let's see if we can do that. Can we increment it? Yep, it'll let me do that too. So I'm going to say that's x plus plus. And then we have to say jump to continue W loop. And actually, no, we can't do that because we have to compare it again. So we don't want to jump up to here. We want to jump up to something like up here. So I'm going to call this while loop. And I'm going to jump to while loop. So there's our while loop. Now, if you're feeling like this is a little bit messy, you're absolutely right. It is a little bit messy, but we're going to clean it up in just a little while. All right, let's see if that worked. Well, it printed, welcome to my program, simple. Did I build this? Yep, I did. Okay, so I moved 0 to keyword. What did I do wrong here? I move 0. I compare keyword x with 10. I jump if they're equal. Oh, no. Well, yeah, I jump if they're equal to continue W loop. Otherwise, I jump to leave W loop. There's W loop. We're supposed to print x. Well, let's debug this. I'm not sure why that didn't work. Let's debug this. Let's go down to that loop. There we go. I'm going to uncomment that one. I'm going to put a comment there or breakpoint there, and let's run it. Okay. So so we move 0 to x. We're comparing x with 10. That's the problem, is that we're comparing x with 10. We need to compare x with 0, don't we? Yeah, because we're going as long as it's greater, let's see what it is, as long as it's less than 10. So compare jump if less than. So I don't want to say equal to, I want to say jump if less than. Or if it's unsigned below. So and let's just do this as signed. So again, I'm saying below. I had equal. I don't know why I used equal. It should be below, less than. I'm looking for less than. Now we don't say below or equal, because if they're equal, it won't, this isn't valid either. So it's below only. So let's make it, okay, let's run it. And it worked. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the moment it becomes 10, we drop out. Now, as I said earlier, this is a bit messy, right? Because there's, first of all, I put in these comments here. We can take those out. but there's still an awful lot of labels. I mean, there's a label here, there's a label here, there's a label here. Yuck. Let's redo that while loop, except this time, let's do it with what I like to call negative logic. And you're going to see how much smaller it is. So I'm going to go ahead and I'm going to copy all of this code right here to this next line, to this line down here. And let's use negative logic. Now, instead of saying below, remember what our while loop looked like. It said less than 10. How about if we check in our assembler code for greater than or equal to, or above or equal to? So that's the exit condition. So what I'm going to do is I'm going to say jump if above or equal to leave W loop. We no longer need that. We actually no longer need that. So we can get rid of all of that. The while loop is still needed. I'm going to go ahead and indent all that. And now we're done. So this is a simpler while loop because instead of using the positive logic, we use the negative logic. We use the opposite of the condition in the while. So instead of checking for less than 10, we checked for above or greater than. If it was above or greater than, we would then leave the loop. And how would that look? That would look something like this in C++. But even that's not right. So by converting it from positive logic to negative logic, and I'll leave this up there for just a second, it'll work. Let's go ahead and build that, and let's run it. Oh, we got a problem. Well, we've got some duplicates, right? So I'm going to call this while loop 2. I'm going to call this leave loop 2. Leave loop 2. Got to make sure we change our jump as well. There we go. Let's run it. All right, worked great. So there's our first loop, which was the messy one, and that goes from 0 to 9. There's our second loop, which is our less messy one because we used negative logic. So again, negative logic is simply taking the positive logic and putting in the all opposite of that. So instead of below, we checked for above or equal to, and then we jumped around all that code. So this is actually, instead of looking to see if we should continue, this is looking to see if we should exit. That's another good way of putting it, I think. All right, so that's our while loop. If you got lost in that, stop the video right now, go back and rewatch it, and you should get it okay. All right, so now let's look at a do while loop. That is another while loop, or that's another type of loop that continues to increment or to go. It continues to go until the condition inside of the while is not true. But a do while loop is not a pre-test loop, it is a post-test loop, which means it's going to do the condition after the loop is actually executed at least once. A while loop can be executed 0 or more times. A do while loop will always be executed 1 time or more, but it'll never be executed 0 times. Okay, it's a post-test loop. It is tested post all of the code. So that's what a do while loop does. Now, I want to really do this from scratch, so let's do it again. So I'm going to move a keyword at x. I'm going to move 10 there. So now instead of counting up, we're going to count down, I believe. Yep, while x is greater than 0. So I move that in there, and that is the x equals 10. And then I'm going to do the do. So what does the do? It prints x. So I'm going to move into RAX x. I'm going to push RAX. I'm going to call print 64-bit num decimal. Call print NL. So that is our print. So that's going to be our cout x. If you're wondering why you're putting yourself through all of this, this is what a compiler does. I mean, much more complicated, but this is basically what a compiler does. It takes these higher level language structures and converts them to machine code. All right, so it does the work. Now, it did not actually do the decrement, so we're going to have to say decrement, a Q word, starting at x. That's the x minus minus. And now we have to do the condition. So I'm going to say compare a Q word, starting at x, with the number looking for 0, with 0. And I'm going to say jump if equal to, or jump if, well, jump if greater than. I want to know if x is greater than 0. So jump if above to, I don't know, what is this, do while loop? Which we haven't created yet. We haven't created that label. So I got to create that label here. And then let's indent everything. Okay. So you can see that the compare and the jump is at the bottom of the loop. After it does everything in the loop, it then does the condition. Now, in this case, we're using the positive logic because the while is at the bottom and we want it to do it again if it's true. So if x is above 0, I want to go ahead and redo the contents of the loop. So let's go ahead and build that and make sure it works. All right, printing with a do while. There's the 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Awesome. So our do while works. The important part of this is that a do while loop does everything in the loop first, and then it does the condition, where a while loop does the condition and then decides whether it should do anything in the loop. So there you go. That is your do while loop. And we didn't have to use negative logic there because the condition was at the bottom. Makes it a lot easier. Okay, so the next thing I want to do is a for loop. Now, a for loop, as you probably already know, is an incrementing loop. Now, in assembly language, there's no such thing as a range-based for loop. That is a programming construct that C++ has implemented to make it more like Python, in my opinion. I don't know if they actually did it for that reason, but Python has the same type of thing. And it doesn't really count. I mean, you can make it count. There is no such thing as that in assembly language. There just isn't. A range-based for loop in C is actually converted to one of these loops. And in fact, probably the loop we're going to do right here. So again, that is a syntax construct or a language construct that was put together to make the language, in my opinion, look more like Python. I hate them, but they work. So a lot of people like them. All right, so let's do a simple for loop. Now here's our simple for loop. What we do is we have an integer I equals 0. So that's the first thing I'm going to do. So I'm going to move a Q word at I with 0. So that's the initialization. That happens only once. So if you remember, a for loop, the initialization only happens once. It never happens again. The first time the loop starts, it does that initialization. All right. Now it asks the question, is I less than 10? So what I'm going to do is I'm going to say compare a Q word at I with the number 10. Now we want to continue if I is less than 10. So I'm going to say jump if below to continue for loop. Otherwise, jump to end for loop. So this is, again, positive logic. And those of you that have paid attention during the while loop discussion, you're going to see that we can make your for loop much smaller, the code in it, by using negative logic. But for now, let's use this positive logic because that's how you look at it as a C or C++ programmer. So jump if below to continue for loop. So here's my continue for loop. And here's my end for loop. So it'll now assemble okay. So what do we want to do? We want to print I. So we're going to move into RAX I. We're going to push RAX. And we'll call print 64-bit num decimal. And call print NL. All right, so we did the C out. Let's go ahead and comment that. I do this all the time with my comments just to keep track. And this one right up here, this should be the I less than 10. Okay. And what happens when the contents of a for loop is done? It increments I. So we're going to say increment keyword starting at I. And then what does it do? It jumps, and we haven't put that label there yet, so I'm going to say for loop. So let's put that up there. Now it doesn't do the initialization of I equals to 0 again, so we have to put that label after that. So that is a for loop in assembler language. Let's make this and build it. And let's run it. And you can see, printing with a simple for loop, it starts at 0 just like a regular for loop does, and it goes all the way to 9. Awesome. However, let's make that for loop simpler using negative logic. So the way that I'm going to do that is I'm just going to copy this down to here. And we have the 0. We have to say you have to put in new labels because we can't have repeating labels. So I'm just going to do that. I'm probably going to delete some of these. Okay. So let's use negative logic. So instead of below, we're going to say above or equal to. Now, if it's above or equal to, you don't want to continue the loop. We want to end it. So we're going to say jump if above or equal to end for loop 2. Now we don't need this one, so we're going to delete that. We also don't need the continue for loop 2. And we do need the end, so we're okay there. So we've just made our code smaller by 2 or 3 lines of code by using negative logic. And there it is. So it works just the same. So that is our for loop. That is how you can use negative logic to make it simpler. And you might be asked to do this on a job interview. More than likely, you'd be asked to do this on an exam if you're in school. But that's how you create those loops, those logical structures that the higher level languages have. Okay, so we went through the standard assembler language loop. We went through a do while loop, actually a while loop first, then a simpler while loop, then a do while loop, which didn't need negative logic, then 2 different types of for loops that did the same thing, one without negative logic and one with negative logic. So I hope you're beginning to see now how crazy people like me that love negative logic, why we love it, because it actually can make code more efficient when you're converting from one language to the other. Hope to see you at our next video.